So when we were establishing the stability of the origin through a Lyapunov function, what we did was we started with a positive definite function. We computed its time derivative along the solutions of the system, and then when that time derivative, when v dot is negative semi-definite, and we concluded that the origin is stable. Okay, and if you want to reach a stronger conclusion like asymptotic stability, then what we had to do was go back to the first step and choose another Lyapunov function. Okay, if such a Lyapunov function exists. It turns out that that's not the only way. There's another way in which we can obtain asymptotic stability by only a negative semi-definite v dot, okay, time derivative of the Lyapunov function. But for that, we have to extend our tool, Lyapunov stability theorem, with another tool which is called Lassalle's invariance principle. Okay, and in this lecture we will be talking about that very powerful and very nice, easy to understand principle or theorem. Okay. To get the main idea with this principle, let's revisit our favorite example, that is pendulum. Consider pendulum with friction. X1 dot equals X2, and X2 dot equals minus A sine X1 minus B X2. This term, minus B X2, represents friction, and we know that from experience, and also we have established it that the origin is asymptotically stable for this system. Okay. Here A, B are positive constants. Okay. Now, for this system, the very first candidate for the Lyapunov function is the energy of the system, total energy of the system, and which have the following form: V of x equals A times 1 cosine x1 plus 1/2 x2 squared. This term represents the kinetic energy, and this term represents the potential energy due to gravity. Okay, and this V of x is locally positive definite. Okay, when we computed the time derivative of this function, energy function, along the solutions of the system, this is what we have obtained. We obtained that v dot of x equals minus b x2 squared. Okay. Now this is just tells us that v dot is negative semi-definite, but not negative definite. That is, for points that are not the origin, v dot can still be 0. For instance, choose x2 equals 0 and x1 something else. In that case, v dot is 0. Okay, but we're not at the origin, therefore v dot is only negative semi-definite. Okay, and this tells us that the origin is stable, not asymptotically stable, if we use only Lyapunov stability theorem. Okay, so that means v dot is only negative semi-definite and as a result, by Lyapunov's theorem, x equals 0, the origin is stable. Okay. Now, by very simple arguments, we will try to extract asymptotic stability of the origin from an only negative semi-definite v dot. Okay? And reasoning goes as follows. So we will now try to say something about asymptotic stability. Okay. Now, of course, asymptotic stability can be achieved by a different Lyapunov function, which we did already in one of our previous lectures. But now we don't want that. We want to stick to this Lyapunov function because it has, let's say, some physical meaning, physical importance. And from this negative semi-definite v dot, we will try to establish, if we can, a spherical stability of the origin. And reasoning is quite straightforward. Okay, so let's try to interpret or figure out the consequences of v dot being never positive. Okay, it's negative sometimes and sometimes it's zero along the solutions of the system. Okay. Now we have a scalar function and its derivative is never positive. Okay, it's always either zero. Okay, it's flat, or sometimes every once in a while it goes down a little bit. Now, so that means that function v, okay, whose derivative is never positive, has to, well, could either go toward minus infinity, okay, or converge to some constant. Now, in this case, for this v, it cannot go to minus infinity. It cannot decrease indefinitely because it's a positive definite function, okay. So it's upper bounded, excuse me, lower bounded by zero. This can never be less than zero, okay. And then, so it's lower bounded by that horizontal axis, and it's also every once in a while it's decaying, so it has to converge to somewhere as time goes on, okay, which is clear physically, although that's not a rigorous argument, mathematical argument, but physically it's quite meaningful, okay, I hope it's convincing. So this therefore implies that because v can never be negative, the x of t has to converge some constant. Okay. Okay, that constant is non-negative. Okay. Now, so that means if you wait long enough, you can take v dot, okay, to be zero, or v of x of t to be constant. Okay. So suppose that we have waited long enough and we have a solution v of x of t, and that solution is produces constant v, okay, when it passes through v. Okay, so this, therefore we can say there has to exist a solution, it's a special solution, and let's call that solution eta. Eta 1 of t, eta 2 of t. That satisfies v of eta of t for all t, okay, is constant, and that constant is c. Okay. Now what we will try to show is this constant for our system, which is, we know that it's not negative, it's either zero or something positive. We're going to show that it has to be zero, okay? It cannot be something positive. So let's see how. So we have, therefore, we're convinced more or less that there is a solution, and when passed through the function v, that solution produces a constant v, okay? And the value that v takes is c. Now, since v is constant, so this 3 bars means that v of eta of t equals c for all t. Okay, that's just a simple notation. So since v is constant, v of t is constant, therefore v dot must be zero. Its derivative has to be zero. V dot eta t has to be identically zero. Now let's remember what v dot was. Okay, so this is v dot, this is the form of v dot. V dot is minus b times the second state component's square. Okay, therefore minus b a2 t square is identically zero for all times. Okay. And that means, since v is positive, eta 2 of t must be zero. Eta 2 t is identically zero. Okay, so v is constant. Okay, we are convinced that there's a constant v there's a solution that produces constant V, okay? And constant V means 0 V dot. And 0 V dot means that the second entry of the solution, second component of the solution, which we denote by eta 2, is 0 for all times. Okay. Now, how about eta 1? What can we say about eta 1? And it's, once you have figured out that eta 2 of t must be 0, it's clear that what eta 1 of t should do. And this is how it goes. Eta 2 of t identically 0. Okay, so we're now trying to identify a solution, which we're denoting eta of t, for which the second component is identically 0. It's 0 for all times. Now, if that's the case, there's not much choice that eta 1 can do, and it follows from the system equation. First of all, if eta 2 is constant, so that means it's not constant, it's 0, but 0 means it's also constant. If it's constant, its derivative is 0. Okay? So eta 2 dot of t must be 0 for all times if eta is constant. So that means, okay, this is our eta 2 dot, and this is therefore what eta 2 dot is. Okay. So that implies minus a sine eta 1 of t minus b eta 2 of t must be 0 for all times. Okay. And now eta 2 of t was 0, therefore we can just forget about this term, and what we have is sine of eta 1 of t equals identically 0, and we are in some close neighborhood of the origin, and in the close neighborhood of the origin, sine of eta 1 of t equals 0, that's one solution, and that's eta 1 equals 0. Okay. So that implies eta 1 of t must be identically 0 in some neighborhood of the origin. Okay. Hence, this solution, okay, which produces constant V, cannot be any solution other than eta of t equals 0, because eta 1 of t equals 0 and eta 2 equals 0. So we're talking about a solution that sits on the equilibrium point. Hence, eta t must be 0. And then we have c equals v of eta t. Eta t is 0, v is a positive definite function, therefore this must be, excuse me. This is v of 0, because eta t is 0, and because v is positive definite, this is 0. Okay? And it's this constant that v must converge to can be no other than 0. Okay. Hence, v of x of t must converge to 0. Then, because v is a positive definite function, then the solution itself must converge to 0. Hence, the origin is asymptotically stable. Is asymptotically stable. Okay. Now that we have established asymptotic stability with only negative semi-definite, not negative definite, but negative semi-definite v dot. Okay, without a negative definite v dot. That's the very powerfulness of Lassalle's invariance principle. Now, let's underline the key point in our arguments, okay, the main observation. And then the generalization of that main observation is what we will now present as Lassalle's invariance principle. So we've made use of following observation. Solutions x of t must converge to the set set of all points. Well, this eta is different than that eta. Okay. Implies e dot of x of t equals 0 for all t greater than or equal to 0. Okay. So when you have a negative semi-definite v dot, all the solutions must converge to a set, okay, where that set is defined as v dot is identically 0, okay, throughout, for all solutions starting from initial conditions that belong to that set, okay. And for pendulum system, this set was the origin. Okay, this set is the origin. Okay, so if we can show that for a general case, this set where v dot is identically 0 is a singleton, the origin, and then in that case, from or with a negative semi-definite v dot, we can establish a spherical stability. Okay. So here is the generalization of our observation, which is due to LaSalle. This is theorem 4.4 from the text. Okay. By LaSalle. Let omega be a closed and bounded, in other words, a compact set, okay, that is positively invariant or forward invariant with respect to the system x that equals f of x. X that equals f of x. Okay, that is, if you start your solution from or within that set, that for all future times you remain in that set. So that's what we mean by positive invariance. Okay, that is x0 belongs to omega, implies x of t belongs to omega for all future times. Okay. Moreover, we let following conditions, all or definitions, all v, be a continuously differentiable function with negative semi-definite derivative v dot of x less than or equal to 0 for all x that belongs to R set of interest omega, okay, are possibly invariant for invariant set. Now that there's no mentioning of V being positive definite. Okay, so this theorem is quite general, but then we're going to see certain corollaries of it that are directly related to stability of the origin. Okay, and then let's introduce this set, which is called E, a set of points that belong to omega, where V dot is 0. Okay. And then we define another set this time. So E is a subset of omega and M is a subset of E. Defined as follows: A dot belongs to E such that x0 equals A dot implies x of t in E all times. Okay. And this N is called the largest invariant set in E. Okay. Now, then x0, the initial condition, starting in omega, which is our positive invariant set. Any solution that starts in omega must converge to this set M defined here. Okay. And in our pendulum example, we have shown that by very simple arguments. We have shown that this set, which is called the largest invariant set in E, is no other than the origin. Okay. Implies x of t must converge to n as t goes to infinity. Okay, now let's see a few corollaries of this theorem, a general theorem. Note that there is no mentioning of stability or stability here, but it has very strong implications or uses for asymptotic stability. Here is the local corollary, corollary 4.1. Okay, this is texts numbering. Consider x that equals f of x with origin being an including point. Let be a continuously differentiable this will be our Lyapunov function. Function on the open set D and containing the origin x equals 0 and beta of x is negative, semi-definite for all points in D. Okay, our open subset. And then let S, okay, set of all points beta for which beta of x equals 0. And suppose that no solution of the system can stay in S for all times. Okay. Which, what we mean by using the word identically, it means for all times. S. Other than solution sitting on the equilibrium point, x of t equals 0 for all times. Then the origin has to be asymptotically stable. Asymptotically stable. Okay. Under a little bit stronger conditions, we can also use Lassalle's principle to obtain global asymptotic stability, and that's corollary. That's the next corollary. Corollary 4.2. Let the above conditions hold. In corollary 4.1, hold with the open subset being the entire space. Rn, and the Lyapunov function being radially unbound. Then the origin is globally asymptotically stable. Now, even though this Lassalle's principle is clearly it's very useful for nonlinear systems, systems that are not linear, but even for linear systems, it's a very powerful tool that can be used. Well, you may wonder why we would need such a theorem for a linear LTI system, linear time-varying system, because we know that for an LTI system, to determine stability, all we have to do is to check the eigenvalue locations. Okay, so that's nice, but for certain situations, you may not know the eigenvalue locations. For instance, you have a system, you know that it's linear, okay, but you don't know exactly the parameter values. All you know is that such matrix are positive definite or positive semi-definite, and then you express your system in terms of those matrices. And then, even though we know those matrices are positive definite, or positive semi-definite, or satisfy certain properties, you don't know them exactly. So, and that means you cannot figure out the eigenvalue locations. In such cases, and in such cases arise more and more as time goes on. Especially recently when people are studying multi-agent systems where you have many systems, the orders are very high and there are many unknowns, okay? In such cases, the nonlinear theorems, nonlinear tools become more and more important to study linear systems, okay? So you should never forget that nonlinear tools can be useful also, and are useful also for LTI cases, LTI systems. Okay, now here is one such example, which I think is quite evident, where we will establish asymptotic stability of a linear system through Lassalle's invariance principle. This is from the book 423. Consider the LTI system x that equals a minus b transpose px. Okay, so this is the closed loop system matrix, and we are obtaining feedback law by solving an optimization problem. Okay, it's a very famous problem. It's called the linear quadratic regulated problem. Okay, where p symmetric positive matrix is a solution of an optimization problem, or in other words, it solves the Riccati equation. Okay, the celebrated Riccati equation with PA plus ATP plus Q minus PBR inverse B transpose P equals 0. So that's the Riccati equation with our symmetric positive definite matrix. This is the matrix that we use to panelize the control input. Well, it's not really important for the problem. And Q equals Q transpose equals 0. And this is the matrix that we use to panelize the step in our cost. Let B, our Liouville function, or Liouville function candidate, be constructed as X transpose Px. Clearly that's a positive definite function because P is a positive definite matrix. And show that the origin is globally asymptotically stable when either one of the following conditions, A, Q is a positive definite matrix. Okay. Okay, not only positive semi-definite but positive definite, and in case B, Q equals C transpose C. Q can be expressed in this form, C transpose C, and this pair CA is also okay. If you cannot remember what observer was, so it's now a good time to go and refresh your linear systems theory. Okay. Here is solution. So we have a Liouville function candidate, and what we do is now we compute its derivative, B hat, so that we can apply Liouville's stability theorem, and also, if necessary, Lassalle's invariance principle. So B dot of x is x transpose px dot plus x dot transpose px. Okay, this is our B, and x dot is given here. That's the closed loop. That's our closed loop system. So let's replace x dot with that term over here, x transpose, and p times x dot instead of x dot. I can write this matrix times x. Likewise, for this x dot transpose, I can write this thing transpose times px, and then everything will be multiplied from left by x transpose and from right by x. Therefore, I can write this thing by x transpose times some matrix times x. And that matrix that appears in the middle turns out to be PA minus BR inverse B transpose P plus A minus BR inverse B transpose P X. Okay, all we did is just replace these x dots with the term coming from the system equation. And then we can write now x transpose times PA plus ATP minus 2PBR inverse B transpose PX We just, here we have PA, here we have ATP, and then we have two of those matrices. And that equals, now we compare this matrix here with the Riccati equation, algebraic Riccati equation, and from there, what we can do is, we can write that as minus Q minus PBR inverse B transpose B, and then we can take the minus outside here, X transpose, and there in the middle we have Q plus PBR inverse B transpose P times X. Okay, and minus sign. Let's call this equation 1. Okay, now A is easy, where Q is given to be a positive definite matrix. Okay, so 1 implies, this equation implies that V dot of X can be upper bounded by X transpose QX. Okay, because this is a positive semi-definite matrix, and here we have a minus sign in front. Therefore, this minus, this term will never be positive, and we can take it out too, and we're left with this. Okay, right, so V dot is always less than or equal to minus X transpose QX. Q being a positive definite matrix means V dot is negative definite because of this minus sign here. So what we have is a positive definite radially unbounded function with a negative definite derivative. By Lyapunov's stability theorem, we have global spherical stability of the origin. Okay, note that we established a spherical stability of the origin of a linear time invariant system without looking at the eigenvalue locations. V dot is negative definite, and V is radially unbounded. Therefore, the origin of the closed system is globally asymptotically stable. Okay. Now let's look at the more interesting case, part B, where we have Q only positive semi-definite. B, where Q equals C transpose. Okay, now again, 1 gives us V dot of X equals minus X transpose C X minus X transpose P BR inverse B transpose P X. Now this is never positive, therefore V dot is negative semi-definite. Why that's never positive? Because, well, this can be written as minus C of X norm squared. Okay. And this term is minus what? Remember that P and P transpose, they're the same. Okay. And that's a symmetric matrix. And then this thing, again, we can write as some norms squared. And that some norm is, it's not as easy as here to see, but it's R minus 1/2. And since R is positive definite, its inverse is positive definite, and also its any power is positive definite. Okay. B transpose PX norm squared. Okay, so here we have a minus norm squared, here we have another negative norm squared. Clearly, that sum is never negative. X is never positive, therefore here is negative, semi-definite. Now, since we have negative semi-definiteness, well, we have stability automatically, but we're not satisfied with stability. We want to show a spherical stability, and for that, what we're going to do, we're going to apply, if we can, Lassalle's invariance principle. For that, we require the set where V dot is identically 0. that S equals the set of all points for which v dot of x equals 0. Then x in that set S implies what? So this equals 0 because that's v dot equals 0. Here we have a norm square, here we have another norm square with minus signs in front. Therefore, if this is 0, then these norms individually must be 0. Okay. And if the norm square is 0, then what's inside is 0. Likewise, what's inside here is 0. Therefore, x belonging to S automatically implies C of x equals 0 and B transpose Px equals 0. Okay, well, here we have R minus 1/2. And since R is positive definite, R raised to the power minus 1/2 is a non-singular matrix. Because it's non-singular, it's a square matrix, non-singular matrix. Therefore, a non-singular matrix times something equals 0 means that something must equal to 0. Therefore, we can forget about that R. We have B transpose P. Well, you can leave R, it doesn't matter. Okay, now here is the claim which will take us eventually to asymptotic stability. Claim is this: no solution can stay identically in S except the one that sits on the equilibrium point. Then x of t identically equals 0. Now here we're going to prove this claim by contradiction. Okay, by which I mean, here's the claim. We're going to say, okay, this claim is false. If this claim is false, that means I can find a solution different than the 0 solution, and that solution of the linear system will stay for all times. It will never leave S. Okay. Okay. Suppose now. Then there exists a solution different than the 0 solution, satisfying x of t belongs to S for all times. For all t greater than or equal to 0. Okay. Now let's see how that gives us a contradiction. So that's a solution of what? Solution of the linear system that we're given. Therefore, it should satisfy the differential equation. So, x dot of t equals a x of t minus b r inverse b transpose p x of t. Now, this term is 0. Why is that? Because we're talking about a solution that's in S for all times. If a solution in S, by definition, v dot equals 0 for all times. V dot equals 0 for all times means, again, okay, from the expression of v dot, that R inverse, this thing is 0. Okay, or in other words, B transpose Px is 0. Okay, and here we have B transpose Px. Therefore, this term is 0 for all times. As a result, whatever this solution is, must satisfy the open loop system equation with input equals 0. So x dot t equals a times xt. And c xt equals 0 for all t greater than or equal to 0. Why c of x of t equals 0? Well, from the same argument, this solution is a particular solution, okay, a special solution which is in S for all times, and if that solution is in S, automatically c of x must be 0. Okay, so we're talking about a solution. Okay, that's not a trivial solution. Okay, that's different from 0. It satisfies x dot equals ax plus it satisfies c of x equals 0. And from those three, okay, from those three equations, we will now, one of them is inequality, we will now obtain or reach a contradiction. Okay, now, this is the differential equation satisfied by x of t, and we can write this, we can write the solution explicitly because it's a linear system, and the solution is x of t equals e to the at state transition matrix times initial condition. Okay, and then c times that x of t, that is c times e to the at times initial condition, must be 0 for all times. Okay, so we have e to the at times x0, that's xt, solution of this differential equation, and then we multiply xt with c, and this thing is 0 for all times. And this implies from observability arguments that x of 0 equals 0 by observability. Okay, remember one definition, observability has many definitions for unit systems. One definition is that if, for an input-free case, if you look at the output of the system, and if the output is identically 0, okay, it's 0 for all times, and if your system is observable, then the state must be state must be at 0, or the initial condition must be 0, or the solution must be the 0 solution. Okay, so that follows by observability. Now we know that the initial condition of this special solution, whatever it is, that resides in S for all times, is 0. Now, this is a linear system, so that means if you start from the origin, okay, you will remain at the origin at all times. X of 0 equals 0 implies that the solution is the 0 solution and x of t is identically 0. And this thing is contradicting our initial assumption here. Okay, x of t is different than 0. Therefore, the claim holds. That is, there's only one solution that can stay identically in the set V equals 0, and that solution is the 0 solution. Okay, and therefore, by Lassalle's invariance principle, all the solutions must converge to that point, which is the origin. Hence, we have lawless flexibility. Therefore, x of t equals 0 is the only solution that stays in S identically. And the origin is globally asymptotically stable by corollary following from Lassalle's